What if I told you that Google's quantum computer has just taken us closer to the edge of the universe than ever before, not with a rocket but with pure quantum power? For the first time in history, we've simulated what happens at the very edge of what we can see. And what Sycamore discovered could change how we understand space, time, and everything in between. This isn't science fiction. It's happening right now. Stay with us, because by the end of this video you'll know what Google's quantum machine found at the outermost edge of reality, and why it truly matters. The hidden power that rules the universe. Imagine a force so pervasive that it makes up nearly 70% of the universe. Yet we can't see it, touch it, or fully understand it. This force is known as dark energy. It's not just a scientific curiosity, it's the key to understanding why the universe is expanding at an ever-accelerating rate. Back in 1998, astronomers studying distant supernovae made a startling discovery. These exploding stars were dimmer than expected, suggesting they were farther away than previously thought. This implied that the universe's expansion wasn't slowing down due to gravity, as once believed, but speeding up. The culprit? Dark energy. Despite its dominance, dark energy remains one of the biggest mysteries in physics. It's not like the matter and energy we're familiar with. It doesn't clump together or emit light. Instead, it seems to be a property of space itself, exerting a repulsive force that pushes galaxies apart. Physicist Michael Turner once described dark energy as the most profound mystery in all of science. It's a force that challenges our understanding of the cosmos and compels us to rethink the fundamental laws of physics. To delve deeper into this enigma, scientists have turned to cutting-edge technology. Enter Google's Sycamore quantum computer, a machine that could revolutionize our grasp of dark energy. Why traditional physics hits a wall? Traditional physics, grounded in classical mechanics and general relativity, has given us remarkable insights into the universe. However, when it comes to explaining dark energy, these theories fall short. One major issue is the cosmological constant problem. Quantum field theory predicts a vacuum energy density that's 120 orders of magnitude higher than what we observe. This discrepancy is the largest known between theory and observation in physics. Classical computers struggle to model the complex interactions of quantum fields in spacetime. They simply don't have the capacity to simulate the vast number of variables involved. As physicist Steven Weinberg noted, the problem is not that we don't have a theory of dark energy. The problem is that we have too many. Without a clear path forward, scientists have sought new tools to tackle this challenge. This is where quantum computing comes into play. By leveraging the principles of quantum mechanics, these machines offer a new way to simulate and understand the universe's most perplexing phenomena. Enter Sycamore, Google's quantum game changer. Google's Sycamore quantum processor represents a significant leap in computing power. Unlike classical bits that are either 0 or 1, Sycamore's qubits can exist in multiple states simultaneously thanks to superposition. This allows it to process a vast number of possibilities at once. In 2019, Sycamore achieved quantum supremacy by performing a specific calculation in 200 seconds that would take the most powerful supercomputers thousands of years. This milestone demonstrated the potential of quantum computers to solve problems previously deemed intractable. Sycamore's architecture includes 53 qubits arranged in a two-dimensional grid. These qubits are cooled to near absolute zero to maintain their quantum states, enabling complex computations with high fidelity. As Google's quantum AI team stated, the very properties that make quantum mechanics so challenging to understand are the same properties we're harnessing in our processors. This breakthrough opens new avenues for simulating quantum phenomena, including the elusive dark energy. With this powerful tool at their disposal, researchers have embarked on a journey to simulate the universe's underlying quantum fabric, aiming to uncover the secrets of dark energy. Simulating the universe's quantum skeleton. Now here's where things get wild. Using Sycamore, Google's researchers managed to do what was once considered impossible. They created a simulation that maps the behavior of quantum vacuum energy. What does that mean? In simple terms, they modeled how invisible quantum forces, constantly flickering in and out of existence, might actually push the entire universe apart. This quantum vacuum isn't truly empty. According to quantum field theory, it's more like a sea of energy bubbling with virtual particles that appear and vanish in a blink. Scientists believe this constant fluctuation could be the root cause of dark energy. But until now, we never had the computing power to simulate those processes in any meaningful way. That changed when Google's team developed a special quantum algorithm that lets Sycamore simulate how these vacuum fluctuations interact with spacetime. For the first time, we could see how tiny quantum-level events might scale up to influence the entire cosmos. That's the magic of quantum computing. It doesn't just crunch numbers. It recreates the very behavior of the universe at its smallest level. One of the researchers summed it up best: we're not just calculating how the universe behaves, we're building a small version of the universe inside a quantum computer. This is more than modeling. It's quantum experimentation on a cosmic scale. Spacetime might be an illusion. But there's an even deeper layer to this discovery. What if we told you that space and time, the very stage where everything in the universe plays out, might not be fundamental at all? Google's simulations are now pointing towards something even more astonishing: the idea that spacetime itself might be a side effect of quantum entanglement. Let's break that down. Spacetime might be an illusion. It sounds unbelievable, but Google's research points to a bold idea. Spacetime, the fabric of our universe, might not be real in the way we think. Instead, it could emerge from patterns of quantum entanglement. In simple terms, spacetime might just be what happens when quantum bits interact in a very specific way. This idea has been floating around in theoretical physics for a while, but Google's simulations are giving it real traction. Their quantum model shows how entangled quantum fields can stretch across spacetime, creating what appears to us as gravity or expansion. In other words, the space between things may not be space at all, it may be a result of how information is connected. Einstein called entanglement spooky action at a distance because it allows particles to instantly affect one another across massive distances. Google's findings suggest that this spookiness might actually be weaving the very structure of the cosmos. When particles are entangled across the quantum field, they might form a kind of invisible web, and that web becomes spacetime. A lead researcher put it like this: it's like realizing the road you're walking on only exists because your feet are connected to it in just the right way. This flips our entire understanding of reality on its head. We used to think of space as the stage. Now it might be one of the actors. The edge of reality. So far, we've been talking about the hidden forces shaping the universe. But what happens when you approach the very edge of what we can observe? At that horizon, things get even stranger. Physics starts to break down. Time stretches. Reality itself wobbles. And with the power of Sycamore, scientists are finally starting to simulate this eerie frontier. What's really at the edge of the observable universe? Imagine standing at the edge of everything we can see, about 46 billion light-years away. Beyond that point, light hasn't had enough time to reach us since the beginning of the universe. It's not just far away, it's unknowable. Until now, we've had no real way to explore it. But Sycamore is changing that. Using quantum simulations, Google's team has begun modeling what might be happening near this edge. At these massive distances, the rules of physics start to shift. Space becomes distorted. Time slows down. And strange quantum phenomena begin to dominate. This is the cosmic horizon, the outer limit of our observable universe. And it might hold the clues to everything beyond. Sycamore allows researchers to simulate how quantum fields behave at this boundary. What they're finding is fascinating. As you get closer to the edge, vacuum fluctuations become more chaotic, entanglement increases, and the structure of spacetime starts to fuzz out. In this strange region, time may not even move the same way it does here. One physicist described it like this: at the edge of the observable universe, reality becomes a blur, like pixels at the edge of a digital photo. We're finally starting to simulate those pixels. These simulations could offer answers about what lies beyond our universe, or if beyond even exists in the way we imagine. The quantum foam beneath reality. We've journeyed from invisible forces to the boundaries of reality. But how do we reconcile all this with our current models? Why hasn't science been able to explain dark energy accurately until now? The problem lies in how we understand the vacuum itself. And that's exactly what we'll tackle next as we uncover the wild world of quantum foam. When we think of empty space, we usually imagine a total vacuum, nothing there at all. But in physics, that idea is completely wrong.
Even what we call empty space is actually alive with activity. This sea of constant action is known as quantum foam, a place where virtual particles are constantly appearing and disappearing in the blink of an eye. According to quantum field theory, every point in space is buzzing with energy. These fluctuations aren't random noise. They're predicted by the rules of the universe. Particles appear in pairs, exist for just a moment, and then vanish again. It's like a quantum dance happening everywhere, all the time, invisible to our eyes but fundamental to reality. Here's the mind-blowing part. This foam might actually be responsible for dark energy. Google's quantum simulation is now letting us model these fluctuations to see how they might cause the universe to push outward. The Sycamore processor was able to simulate how billions of tiny quantum fluctuations create a steady large-scale pressure on the fabric of space, possibly explaining why the universe expands. As theoretical physicist Frank Wilczek put it, empty space is not nothing. It's the most complex thing you can imagine. And now, for the first time, we're getting a look inside of this complexity, not just with equations, but with real simulations. We've now seen that space isn't empty, and time might not be steady. But there's still a big question. Why hasn't the universe ripped itself apart with all this energy buzzing around? The answer could lie in how this energy balances out. And that brings us to one of the strangest riddles in all of science. Why the universe is expanding just right. Why the universe isn't ripping apart. Here's a paradox. If quantum field theory is right, the vacuum energy in the universe should be huge, so massive, in fact, that it would blow the universe apart in an instant. But clearly that hasn't happened. We're here. Galaxies exist. So what's going on? This issue is called the Cosmological Constant problem, and it's one of the biggest unsolved problems in physics. The theory predicts a vacuum energy that's 120 times greater than what we actually observe. That's a 120 order of magnitude difference, the biggest mismatch between theory and reality in all of science. Google's simulation is giving us a possible answer. The quantum algorithm they built seems to show that many of these fluctuations cancel each other out. Instead of adding up to something huge, they mostly neutralize. What's left behind is just enough energy to expand the universe gently, not violently. Think of it like waves in a bathtub. Most of the ripples cancel each other out, leaving just a gentle rising tide. That tide might be the small leftover pressure we experience as dark energy. Sycamore's power lets researchers run this simulation at scale, giving us a view of how vacuum energy might be self-balancing. A physicist from the team summed it up. Quantum computing might finally explain how so much energy ends up doing so little. That little bit of leftover pressure, all it takes to drive the expansion of the universe. And now we're finally beginning to see why. So far, we've seen how quantum computing simulates the vacuum and solves some of the universe's deepest puzzles. But how exactly does a quantum computer pull this off? It's more than just faster computing, it's a new way of thinking. Let's explore how Sycamore was designed to simulate dark energy and what makes it unlike any computer the world has ever known. The Sycamore simile and breakthrough. What makes Sycamore so special isn't just its speed, it's how it thinks. Traditional computers run through problems step by step using bits that are either on or off, ones and zeros. Quantum computers like Sycamore use qubits, which can be both 1 and 0 at the same time. That's called superposition. But the real magic happens when these qubits interact through a process called entanglement. Qubits share information instantly, even across large distances. This means Sycamore can explore a huge number of possibilities at once, making it the perfect tool to simulate quantum phenomena like vacuum energy in spacetime. To run the dark energy simulation, Google's team designed a quantum circuit that mimicked vacuum fluctuations, those tiny virtual particles popping in and out of space. This wasn't just programming. It was building a mini-model of the universe using pure quantum logic. Each operation on Sycamore involves quantum gates, tiny pulses that change a qubit's state. These gates are combined in layers to form quantum algorithms, like building Lego bricks into a castle. The result? A simulated space where the laws of quantum physics unfold just like they do in the real universe. As a lead developer said, what's impossible for classical machines becomes natural for quantum ones. That's the power of Sycamore, not just solving problems, but opening windows into realities we could never reach before. Now that Sycamore has cracked open a door into the quantum structure of the universe, what's next? The current simulations are groundbreaking, but still limited. We're talking microseconds of data, simplified models, and early-stage algorithms. But all that is about to change, because Google has already planned the next step in quantum evolution. Limitations still remain. As powerful as Google's Sycamore is, it's not perfect. The simulations we've talked about are still early tests, small glimpses into what could become full models of the universe. Right now, Sycamore can only maintain its quantum state for a few microseconds. That's a blink of an eye when you're trying to simulate cosmic evolution. Another challenge is error rates. Qubits are incredibly sensitive. They can lose coherence from the slightest environmental noise, heat, vibrations, even cosmic rays. This makes long, complex simulations unstable unless errors are constantly corrected. Google uses error-correcting algorithms and better hardware designs, but the tech still has a way to go. The models being run, then, are also simplified versions of reality. Real quantum fields are incredibly complicated. To simulate every aspect of them would take more qubits than current machines can handle. What we're seeing now are starting points, blueprints, not final answers. But the progress is undeniable. As Google's engineering director Hartmut Neven said, each simulation gets us closer, but we're still working with approximations. This is a long journey, but we've taken the first real steps. And those steps are already reshaping our understanding of the universe. The beauty of science is that it moves forward, especially when the world's best minds come together. Google isn't working alone. Some of the brightest institutions on Earth are now joining forces to push these simulations to the next level. Together, they're trying to do something extraordinary, build the first working model of quantum gravity. Collaborations that are redrawing the cosmic map. Google knew from the start that it couldn't crack the secrets of the universe alone. That's why it's teamed up with places like Caltech's Institute for Quantum Information and Matter and Fermilab's Quantum Science program. These partnerships are combining the strengths of quantum engineers with top-level theoretical physicists. The goal? Simulate aspects of quantum gravity, the elusive theory that merges quantum mechanics with general relativity. It's been called the holy grail of physics. Einstein gave us the theory of gravity. Quantum mechanics describes particles and forces at the smallest scale. But bringing the two together has never worked, until now. By designing new quantum algorithms, these teams are aiming to simulate how quantum fields might actually cause spacetime to bend, ripple, or emerge entirely. They're testing everything from the behavior of entangled particles in curved space to dynamic scalar fields that might replace the cosmological constant. One researcher explained it best. We're not just testing equations anymore. We're watching the universe come to life in a lab. The simulations aren't just theoretical. They're producing data that can be compared to real-world astronomical measurements, closing the loop between math and observation. As we step into this new era of scientific possibility, one question lingers. What lies beyond the known? With more powerful processors, deeper simulations, and better models, we may soon discover the true architecture of reality, engineering reality itself. And one of the most shocking revelations from this research is already challenging everything we thought we knew about what space and time actually are. The new frontier, engineering reality itself. It sounds like science fiction, but it's real. Google's quantum simulations suggest that space-time might be a result of quantum entanglement, not a separate thing. That means space and time, the fabric of everything we know, could be emerging from deeper quantum processes. This is one of the most mind-blowing ideas in modern physics, that space-time isn't fundamental. Instead, It's built from the way particles and fields are entangled across space. If that's true, then reality as we know it is like a hologram, a surface projection of deeper quantum connections. Google's quantum circuits are helping scientists simulate what this would look like. They've built models showing how changes in entanglement affect the shape and curvature of simulated space. This suggests that gravity, motion, and even causality could all come from patterns in quantum information, not from separate forces. A physicist working on the project put it this way: "It's like realizing the ocean is just the pattern made by billions of water molecules dancing in sync. Space and time are that dance." That's not just poetic. It's potentially the start of a new way of building physics from the ground up. What comes next? So we've seen where we are, but where are we going? Google's team isn't stopping with Sycamore. Their roadmap points to even more powerful machines, more qubits, longer coherence times, lower error rates. All of this adds up to one thing. The future of quantum simulations will be able to test the most ambitious theories in science, including the very idea of a multiverse. Google's next big move is a processor called Bristle Cone. It's designed to go beyond Sycamore with 72 qubits and better quantum error correction, allowing it to run longer, more complex simulations. This could stretch coherence times from microseconds to milliseconds, a 1,000-fold leap that would transform what's possible. With Bristle Cone, scientists aim to simulate not just parts of the vacuum, but full quantum field models. This opens the door to testing different theories of dark energy. For example, one is quintessence, where dark energy changes over time instead of staying constant. Another idea is that Einstein's equations break down at cosmic scales and need updating. Quantum computers can now test these wild ideas. Even more ambitious, simulating string theory landscapes. This theory suggests our universe is just one of countless possibilities. Each one has its own vacuum state, its own laws, its own expansion rate. Until now, there was no way to explore this. But Google's simulations could soon let us map these cosmic possibilities. As one researcher put it, for the first time, we might be able to simulate not just our universe, but other possible ones. That's not just a leap in physics. That's a leap in imagination. It means we're moving from asking what is to what could be, from modeling the vacuum to unraveling space-time. Google's quantum computer has started a new chapter in our quest to understand the universe. While we're still in the early stages, the direction is clear. We're building the tools that may finally connect the smallest pieces of reality to the largest structures in the cosmos. The edge of the observable universe is no longer just a limit. It's a gateway. So Google's quantum computer may have just cracked open a new way to understand the universe itself. From quantum foam to the edge of space-time, we're only getting started. If that amazed you, make sure to like, subscribe, and hit the bell. Thanks for watching, and see you in the next journey.